So today it's a pleasure to have here with us, at least on a screen, Victor Gorbenko. Many of us remember him because he spent many years at NYU that I hope he didn't hate, that remembers with some fondness. He's now in Stanford and he will talk about new tools for fundamental cosmology. So, thank you.
Yeah, thanks, Massimo. It's always a pleasure to be back at NYU, even virtually. Indeed, today we'll talk about some new work on cosmology. Let me start with reviewing very briefly the state of the field and with a short motivation. So modern cosmology is a remarkable success of both theoretical and experimental physics. I think it's very impressive how much of a detailed information we have about the history of our universe up to really the first few seconds of its evolution. As you see on this image, I have a schematic drawing of our history of the expansion of our universe. And the point of this image is that the very beginning, what we refer to as the origin of the universe, that of course remains one of the biggest mysteries in modern science. So the earliest period of the evolution of the universe to which we have any access to is called inflation. Inflation is a period of exponentially fast accelerating expansion of space. Let me review very briefly what this period of inflation is. So in fact, to create inflation, you really need very few simple ingredients. All you need is general relativity with positive cosmological constant and the clock field that we sometimes refer to as the inflaton. So putting the first two together gives us a space-time, which is called de Sitter space, or in fact, it's approximately de Sitter space, but this approximation will not be very important for us. So we will take the scale factor. For the purpose of this talk, we'll consider the scale factor, which really grows in time exponentially. What is important in inflation is that there is the clock field that undergoes quantum fluctuations. And according to this inflationary paradigm, all the structure in the universe that we observe around us originates from these quantum fluctuations of this inflaton field. So here there is another cartoon of this inflationary period. Now time goes upwards, and basically what happens is that we can think of the metric being exactly of this simple form over here, but the clock field, which tells us when inflation ends and when we transition to the next period of cosmological expansion, it's not exactly smooth, but it has some quantum fluctuation to it. These quantum fluctuations by expansion and later by gravity get amplified to macroscopic scales and form pretty much everything that we see around us, or at least give the seed to this formation. So let us discuss briefly what are the observational signatures of inflation. How do we actually gather experimental information about this period of space, period of evolution of our universe. So one can think of the universe as a one big collider event. And not only it is a collider event, but also universe filled itself in with a whole bunch of detectors. Now, upcoming cosmological and astrophysical experiments, they will provide us an enormous amount of new data about these primordial fluctuations. So here I listed a few of those experiments. Historically, most of information about the inflationary period was coming from cosmic microwave background radiation experiments. There are some upcoming experiments that are listed over here. More recently, the community was switching a lot to so-called large-scale structure experiments. Large-scale structure is basically the distribution of galaxies, or even more so galaxy clusters in the universe. Those distributions, they also trace the information about this primordial quantum fluctuations created during inflation. There are even more futuristic, I would say, experiments based on the 21 centimeter line observation. It's a line of neutral hydrogen that is also contained in abundance in our universe. The main points that I want to make that there are many different experiments. Some of them are being designed, some of them are already collecting data, some of them are being proposed, that there are many different technologies, and altogether they will deliver a large amount of new data. As some measure, let me pick some observable that's sort of relevant for my discussion, which is a three-point function, three-point correlation function of this primordial field. This is something that we call non-Gaussianity, and it is labeled by a parameter called FNL. In particular, there is, so it also depends on kinematics, on positions of these 3 points. There is some kinematic limit that is called FNL local, which is just some number, some dimensionless number that is normalized according to some conventions. So current bound, so for now, the measurement of this number is consistent with 0, okay? And the best bound is coming from the CMB experiment called Planck, and it's equal to 5. Just the point of this slide is that this future experiment, they're going to improve the bound on this particular number on as much as 2 orders of magnitude, which is quite impressive. There are not so many fundamental observables in physics on which we're going to improve the experimental results so well. So why, for me, where my motivation to work on theoretical cosmology now, it's coming from 2 basically different directions. One is this upcoming experimental progress that I just described, and the other is basically the opposite. It is the progress in our understanding in more formal fields of theoretical physics, in which we're making lots of progress in understanding quantum fields and gravity in anti-de Sitter space, which I will introduce in a moment, and as well as developments in the physics of Hawking radiation and black hole evaporation. And similarly, the applications of our work, they're also twofold. On one hand side, I hope that they will provide some input for experiments, okay? And on the other hand, they are giving us some hints for building this fundamental theory of cosmological spacetime that eventually we hope will be the complete theory of the origin of the universe. Okay, before so this talk is going to be dedicated to this right half of this slide mostly, but before I go into this technical details, let me just briefly summarize and highlight the main results. So the talk will consist of 2 parts. In the first part, we will discuss quantum field theory correlators in de Sitter space, and this is an ongoing work with Lorenzo De Petra and Shota Komatsu. And in this part of the talk, we will see that any perturbative calculation of this inflationary correlators of this primordial quantum field can be reduced to calculations in the anti-de Sitter space that I will introduce in a moment. And this gives a major technical simplification. Okay, so we will obtain some explicit results for some example theory that haven't been calculated until now. And maybe even more importantly, we will see some general properties that these correlation functions have to satisfy as a consequence of symmetry and unitarity of our theory. Then I will switch gears, and in the second part of the talk, I will describe, in a sense, an opposite regime. We will talk about non-perturbative gravitational effects. So this results of this paper that we wrote with Yiming and Huan last year. And there we will introduce a simple toy model of inflation where we can have control over these non-perturbative gravitational effects. And we will see that an important one is something what we call a bracket wormhole, which will be some space-time connection between Bra and a ket of the wave function of the universe, if you wish. So this contribution in this model, it basically replaces more well-known Hartle-Hawking state. And importantly, it gives some sizable corrections to the spectrum of primordial fluctuations, at least within this model. And it also suggests some hints on a more fundamental understanding of de Sitter entropy. And then I will conclude, and if there is time, discuss some future directions. Okay, great. Let me start with the first part of the talk, unless there were some questions about the introductory part. But feel free to interrupt me if something is unclear, or especially if there is some technical problem. Okay, if no, let me move on to this first part of the talk. Good, so as we discussed before, in inflation, the metric approximately takes this form. In actual inflation, this Hubble parameter depends on time, but for this part of the talk, we will take it to be constant, okay? And this is what's called the de Sitter space. We also take the de Sitter limit at the level of all kind of interactions. This is also broken in actual inflation, but these corrections are not going to be important for what I'm discussing now. So we're considering the simplest case, which is the de Sitter spacetime. We can think of it as the most symmetric, the simplest model of cosmology. Moreover, in this de Sitter space, we will take the following Lagrangian. So I will take two fields, this field phi and the field sigma. Let's think of phi as like a lighter field. Maybe this is this primordial inflaton field that we eventually observe. And sigma is some heavier field with which it interacts through a cubic coupling. Okay. Then we're interested in calculating correlation functions of this phi field localized on the what we call reheating surface, right? This is where inflation ends. So here on this picture again, time goes upwards, and this is my exponentially expanding part of the universe. And here we transition to some other cosmological epoch, okay? Our observer is, of course, somewhere here, but our satellite or something can basically, in this idealized approximation, collect information directly from the reheating surface, okay? This is where our observable is localized. So we're interested in calculating correlation function of this field phi. In particular, let's focus on this 4-point function. Okay, and there is a simple contribution, basically the leading non-trivial contribution to this 4-point function. It comes from this exchange diagram, just a 3-level diagram of exchange of a field sigma. Okay, somewhat surprisingly, even this simplest diagram until recently hasn't been really calculated in any analytic form. And our goal is to develop tools for doing this kind of calculations. And we want to do it in the most straightforward way possible that will also highlight the universal property. So to better explain what I mean by this problem, let's take a short detour and just discuss a similar calculation in flat space that I think most of us are familiar with. Okay, so we take the same Lagrangian and put it in just in flat Minkowski space and calculate again the 4-point function or the amplitude of scattering of this 4 phi particles. This is, of course, an elementary calculation, which results into this simple answer where S is the center of mass Mandelstam variable. Good. Even this simple calculation already contains some interesting physical information. For example, for physical values of momenta, this variable S takes a value that's larger than 4m phi squared, and if the mass of particle sigma is heavy enough, then this answer violates unitarity. It just blows up. Okay. Well, in flat space, we know how to remedy this. We need to resum so-called bubble diagrams. Okay, so we need to recalculate this set of diagrams. So this is sigma, 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 this is phi, phi, sigma, sigma, phi, phi, okay? So I use the same lines for these two particles. The answer is, of course, well known. What happens is that this self-energy diagram, this bubble, goes into the denominator. There is some expression that I wrote here, doesn't really matter what is in details. What is important is that this self-energy diagram develops an imaginary part due to this phi particles propagating off shell. So now, if we draw the analytic structure of this amplitude in the complex S plane, so this physical region is located over here, and there is the cut that originates at 4 and 5 square. This cut gives an imaginary part of amplitude. So the pole, this worrisome pole that was for physical values of S of the 3-level answer, it goes down in the complex plane. And instead of something that blows up, we get a nice resonance shape for our amplitude. Okay. And then the imaginary part of the amplitude has to be positive due to unitarity. Again, unitarity also imposes this condition that the absolute value should be smaller than 1. There are some analyticity properties of the amplitude, and all of this really follows from this very simple calculation. Good, so we want to obtain some similar level of understanding for these inflationary correlators. But you may ask, why is it so much more complicated? Why don't we just do and repeat the same calculation in the Sitter space? So let's review how this calculation would go. First of all, because now we're not computing some scattering element, but we're computing the correlation function, we need to use so-called in formulae. So this on its own is not something too complicated. Basically, we take our state of our quantum fields, evolve it with the Hamiltonian, then we insert our operators, and then we evolve the state backwards in time, in a sense. So we can say that we evolve the Bra and the ket of our wave function. So now we're going, because we're doing just perturbation series, we're going to do some weak contractions. There will be weak contractions on this side, or between two Hamiltonians. And this will involve 3 types of propagators. Okay. This means that our diagram basically splits into sum of 3 diagrams. Now, each of this propagator turns out to be some sort of hypergeometric function. Good. Now, what is this? Let me explain some notation. So there is this variable S over here, which is, I'm working for now in a position space. This S just encodes in some way the distance in the Sitter space. Here I went to conformal time that will be convenient for the rest of my talk, that just related to the FRW time I introduced the buff in the following way. Now, this parameter nu that also labels the propagator, it is related to mass of the particle in a simple way. One thing to know that in the Sitter space and hence on inflation, there are 2 kinds of particles depending on whether this parameter nu is real or imaginary. They're related, I mean, roughly these are particles that are lighter than Hubble scale or heavier than the Hubble scale. Okay, good. So now this diagram of ours is basically some convoluted integral of these hypergeometric functions. And the problem is really there isn't a simple Fourier transform that would factorize this integral. Okay, and analytically calculating this integral is not a simple task. So let's remember that the simplification in flat space was just coming due to the fact that we could go to momentum space, and that was using the Poincare symmetry of Minkowski space. What is the symmetry of the Sitter space? Well, it turns out to be SO1, D plus 1, where the D is number of spatial dimensions. Okay, so we consider D plus 1. Dimensional. Good, and importantly, the reheating surface in the limit that we consider is left invariant by this group. So basically, we expect our correlation functions in the limit that we consider to transform nicely under the symmetry group. So this prompts us to take another detour and consider another problem, which is somewhat similar technically. That is the problem of calculating correlation functions in Euclidean anti-de Sitter space. Okay, so Euclidean anti-de Sitter space, it's a space-time that has the same isometry group as Lorentzian de Sitter space. And in this representation of mine, metrics are related in a simple way. So you see here I have this metric of this Euclidean anti-de Sitter space. It is formally obtained from de Sitter space by replacing time with this radial I times this radial coordinate z, and also changing the h to ik. So we can think of this Euclidean de Sitter space as basically inflation that goes sideways. Okay, so it is a fully Euclidean space. There is no time, but there is this radial coordinate along which the space-time also expands. So there is a boundary of this Euclidean de Sitter space. Here there's a boundary, which is basically an analog of the reheating surface, for my point of view. Good. So the point is that recently there are many powerful techniques that were developed for doing calculations in this de Sitter space, largely in the context of ADS-CFT correspondence. And in particular, there is so-called split representation, which is the propagator. Now there is again some propagator in this de Sitter space, some other hypergeometric function. That's not very important. The important thing is that there is the analog of Fourier transform that basically factorizes this propagator in some product of plane waves. Good, and this allows basically simply to calculate a related diagram in de Sitter space. So there is some Macy expression. Let me not go into it. There will be similar expression in the Sitter space that we will discuss in details. Good. So the analogous problem was solved in ADS. So let's go back to the Sitter space and remember this diagram that we're trying to calculate, or in particular some of these three diagrams. And the point is that there is a following trick. That we can do a certain analytic continuation of any Feynman integral on the Sitter space that reduces it to some sum of ADS-like Feynman diagrams. Okay, so this analytic continuation is specified over here. So remember that we have two types of interaction vertices. Some of them are located on the left part of our contour, of our in time contour, and some are on the right. So basically, we work in position space, and for each Feynman diagram, we rotate the times associated to these integrals in the following way. We rotate left times in one direction, right times in another direction. It is a property of any Feynman diagram in the Sitter space that this analytic continuation can be done without hitting any singularities. Good. The result of this procedure.
Sorry, Victor, may I ask you? So in AD, like in Euclidean ADS calculation, you're referring to there. It's not in calculation, right?
No, it's a Euclidean calculation. There is only one kind of propagator. So there is no state. We're just computing Euclidean path integral when we calculate these correlators.
And so this analytic continuation which you are making, you start from in calculation, and that it brings you to conventional Euclidean calculation without any in.
Yes, yes. It's not really like an ordinary weak rotation or something. It is some just formal way of analytically continuing the integral. Any other questions?
Yeah, Victor, I have a question. So at the top of the page, you have these three types of propagator. I missed the distinction between them.
Yeah, sorry. Okay, let me. I went fast through them. So they are the same functional. They have the same functional form, and they only differ by an I-epsilon prescription. So in the Sitter space, because it's a Lorentzian spacetime, this function develops a singularity on the light cone. And the way the three propagators are different are how we go, from space-like to time-like separation between the points. Okay, so there are different I-epsilon prescriptions. And it's important that these I-epsilon prescriptions are organized in a way that this particular analytic continuation never crosses any of the singularities of the Feynman diagram. Okay.
But so after analytic continuation, you still have three different propagators? Or in AD?
Yeah, let me explain what I have after analytic continuation, okay? So the statement is the following. The punchline is that any theory on Lorentzian de Sitter space in which we can calculate in and correlation functions can be replaced by a theory on Euclidean de Sitter space with two sets of fields, okay? So with a double set of fields that here I just write for a single theory for a single scalar field gets replaced by a theory with two scalar fields that I call here phi plus and phi minus. So you see it's a somewhat more complicated Lagrangian. What are these fields phi plus and phi minus? So to define a theory on Euclidean anti-de Sitter space, we need to specify boundary conditions this boundary of anti-de Sitter space that, remember, I was calling what is my analog of reheating surface. Okay. So it is part of a definition of the theory in anti-de Sitter space. So these two fields, they have the same mass as the original field, well, up to some overall factor actually over here, but they have opposite boundary conditions. Okay. So now, each of these fields has just one propagator because it's Euclidean series, there's one propagator. But there are in total, each Feynman diagrams contains two sets of lines because phi plus and phi minus fields, they interact. Okay, they decouple at the level of kinetic term, but through the interactions they miss. So that is the claim that any Feynman diagram generated by this Euclidean Lagrangian on the nose reproduces all the Feynman diagrams of this de Sitter theory.
And sorry, this is a non-unitary theory in the
Good. Yes, this is what I was just going to discuss in a moment here. So it's known that usually in anti-de Sitter space there is some range of masses for which both boundary conditions are allowed. Here we are generically outside of this range of masses. So this theory doesn't really make any sense. I don't think it can be interpreted in Lorentzian anti-de Sitter space because indeed it's completely non-unitary. But here we never go to Lorentzian anti-de Sitter space. We always stay in Euclidean anti-de Sitter space. So notion of ADS unitarity is irrelevant for us. Okay, so more is allowed in the Euclidean theory.
Sorry, Victor, what is nu again?
Nu, it's here.
Yes. Thanks.
My label for the mass, basically. For heavy fields, nu is real. And for light fields in de Sitter, nu is imaginary. This is the notation.
But also, apart from being in the kind of wrong mass range, also your action looks explicitly
Yeah. Well, also
so
look, there is a relative minus sign between kinetic terms.
Right.
One of these fields is a ghost. That's even worse.
So it's not nothing like a unitary theory.
There's nothing like a unitary, but this Lagrangian is a Hermitian, so it's a real theory. If you complex conjugate it, that it goes back into itself, which is okay. You can check. Good. So the proof of this statement, it goes diagram by diagram. Let me just skip it. So there is no non-perturbative statement at this point, but to all in perturbation theory, this is just true. And this basically allows us, because as I said, these diagrams with the topology that we're interested were calculated in anti-de Sitter space, we can basically almost immediately write down the answer in de Sitter space. So this answer looks a bit like
one question. The left propagators and right, are they different?
Well, as I said, they're the same hypergeometric function, but they have different epsilon prescriptions. So when we do this analytic continuation, analytically continue differently.
Yeah, but do you have 3 or 2 different types of propagators? We have left,
in
right,
the original
left,
theory, I had 3. In the final theory, I have 2. But the claim is that the particular it's the sum of these 3 diagrams that always contributes to any physical answer contributes to the sum of all the diagrams at the same level of perturbation theory of this Lagrangian.
And sorry, in your diagram, I didn't see a label for the phi propagator. I mean, the ones that end up on the reheating surface.
There's a phi's on the external lines, and there's a sigma on the.
So the propagators for phi and sigma, are they left, right, or mixed?
Yes, good. So we need to. I didn't say how do we identify the sources. And basically, the idea is that in this theory, we just need to calculate the correlation function of phi minuses. Okay. So the Euclidean correlation functions of just phi minuses in this ADS theory, this maps into the correlation function of phi's in de Sitter theory.
So Victor, at the point where nu vanishes, so m is d over 2h or something, then this Lagrangian becomes strongly coupled, no?
Yeah, I did. There is okay. There is something special happens at this values of nu equals 0, and yeah, we need to. So the statement is that if you look at any expression, that it's any answer is eventually regular, but one needs to check more carefully what actually happens, like why I do not have a very good physical picture of what happens. So, you know, there shouldn't be anything special at that point from the point of view of this theory. And then your final answer, so there is enough zeros in the numerator, you know, to cancel these zeros in the denominator. In other words, like a canonically normalized fields, it will go here in the interactions and everything will be smooth, but it's not very explicit. Over here. It's not manifest, but it shouldn't be a concern. The idea is that everything is eventually analytic in this new.
Okay.
Okay, good. Any other questions? Let me. So I think yeah. So even if we look, you know, at this final answer, there are no news in the denominator or something like this. So they somehow miraculously cancel in the process of the calculation. Good. So let me explain in some detail what is this answer, because it looks a little bit like some mess, but there is just a rather trivial factor here where dependence on coordinates is encoded. Okay. Then there is this object here, and also here as the same. This is something called conformal partial wave. So this is this z and z bar. These are also functions of my coordinates. Okay, this conformal cross ratio. And the point is that these conformal partial waves, they are fully fixed by symmetry and the kinematic. So there's no dynamical information that's encoded in them. These are some functions that are known explicitly in some dimensions. In some dimensions, they're only known numerically, but they've been very actively studied in the context of conformal bootstrap, for example. So, you know, it's a function whose properties and the numerical tabulation is very well understood. Dynamical information is really encoded in these factors over here. And most important of them, okay, this is really some subtraction that will even disappear in a moment. But the most important of this is this factor over here. This is really the analog of the flat space calculation that we did. This is really the contribution to the correlation function, which is the analog of the flat space amplitude. Okay, you will see that here there is some simple map between. So this label contains the mass, and this variable nu prime is basically an analog of the energy variable in the flat space calculation. So these conformal blocks, and in a sense also these gamma functions, this is some decoration that we need to go through to extract really the simple form of the answer. Okay. Note that it also has the same problem, that if we take this particle sigma to be heavy, so we take real nu, this answer blows up, which also in the zeta space violates unitarity. So we know what to do. Guided by the flat space intuition, we need to resum these bubble diagrams. Again, with our techniques, we can do it. And what happens now, again, you see that there is this my conformal block. There's these factors that basically go along for the right. Important thing is that this f of nu, this basically spectral density that at the tree level had a simple pole, it develops this, this bubble function. So this b is the result of the calculation of the bubble. In the zeta space goes in the denominator, and importantly, it is some messy function that's saying d equal 2, there is some explicit expression. What is important that it develops an imaginary part. Okay, so very similar thing to the flat space happens. Long story short, we represented our correlation function as an integral of a single variable, okay, of some function rho of nu times this kinematic factor called the conformal block. Good. Let us, in flat space, we learned quite a bit from the analytic structure of our amplitude. So let's see what do we have here in the zeta space. Namely, so on this plot, I draw the analytic structure of this function rho of nu. It's a bit more familiar, nicer, I would say, to draw it as a function of this other variable delta, which is a 0, 2 plus I nu. So real nu now goes upwards, right? So my integral that goes from minus infinity to infinity, it actually goes along this imaginary line. Good, so there could be some poles over here associated to light particles. These poles, due to sigma field that I focused on, they got displaced in the complex plane by some widths, which is afforded the coupling constant squared. So that is basically the result of this contribution. And then an interesting statement is that this function is actually a Dolorus and perturbation theory is just a meromorphic function. So the analytic structure of this rho of nu, it turns out to be much simpler than, say, of a flat space amplitude that generically develops some cuts. We also understand at this level in perturbation theory, we understand all the poles of this function. They come in some triplets, which basically has a meaning of some, each of this pole is related to a pair of phi fields, okay, in a way that I can explain. An important feature of these poles is that in the so-called squeezed limit of a correlation function, which has some observational relevance, each of these poles give a power law contribution, okay? Where it's, so the squeezed limit, then we take our 4-point function, say in momentum space, and the short momentum, and say we take this square looking configuration on the sky. And then in this limit, each of these poles will correspond to a power law contribution.
So what happens in the flat limit to this function?
The flat limit, you basically go over there, yeah. A flat limit is nu to infinity, and also if we want to get something non-trivial, we also want to get mu sigma to infinity, and then this basically maps into S. So roughly speaking, that's how you reproduce it. Or nu squared maps into S.
And the cut arises as what, from many poles? Or
yeah, I think as the usual thing, as in the flat space limit of ADS, the cuts, they arise from these poles coming together. But it's not, it's not trivial. It's an interesting question to see how the flat space limit really arises. Like at the tree level, it's simple. At the loop level, it's something funny goes on. I think all these poles, they individually should go to infinity and merge, because you see my physical flat space limit is over here, but all my singularities, they're on real line. So it's not obvious how they will, but it should be true, but we didn't yet do it at the level of equations, but one should do it.
So Victor, so your B, you have it written some up there. Can you please lower to see it?
B, yeah, that's like in D equal 2, where it's a bit simpler than it's written, yes. In D equal 3, it's some terrible mess of special functions that, again, we can write explicitly, but it will take a page.
And you said that it's such that it doesn't have any cuts?
This object, yeah, it's also meromorphic. Yes. All of these functions are meromorphic here. And that follows, this follows from the fact that in ADS, they have to be meromorphic, and that is due to the fact that in ADS, there's operator product expansion, which converges. Now, in the theta, there is no operator product expansion, but because we reduced our theory to this fake non-unitary ADS theory, and OPE arguments do not really rely on unitarity, at least in perturbation theory, we also know that it has to be meromorphic. That's how the argument goes.
Yeah. And related question, let's say in the first bubble, I had I had one loop correction, not the bubble correction, but the loop correction, which you didn't sum up, right?
Sorry,
let's say in this first loop
here.
Yes, I had next correction, the loop correction. It would be like large MQCD would be subleading 1 over n, right? So here is the argument why you're ignoring those? Or?
Yeah, this will be a perturbative again. Argument basically is the same as in flat space, that near the resonance, we just need to, to get the leading contribution to the width, we just need to resum this bubble diagram. So there is a correction to there is also like G squared times this, let's call it, I don't know, B2, right? Where B2 is, sorry, not G squared, G to the fourth, right? B2, where B2 is this diagram, but it's a next order. It's like a correction to the width that's perturbative, right? And I think you're asking, do we have a control over this kind of diagrams? And the answer is that here near the resonance or in the physical region, yes, I know how to estimate these diagrams and to say that they do not blow up. It's a bit more tricky to answer, how do they behave everywhere in the complex plane? I guess all we know at this point is that there should be some meromorphic functions, but their asymptotic behavior over here is not really understood yet. But we can see that they're bounded on the physical region. Does that answer your question?
Well, yeah, I didn't get a clear picture. The reason why is because that diagram that you just drew is the same order as the next one. That is a double bubble that you included. I understand that you're summing up the bubbles, but if I don't sum, then the one with the red that you just drew is of the same order as the next one, double bubble.
Yeah, but this is the same as in flat space because there are these propagators that basically go on shell, right? So each of these, so it's important to resum these bubbles. So, every time I'm far away from the red cross, I don't need to resum. I just work to leading order in perturbation theory. I need to resum only when I'm close to red cross. When I'm close to red cross.
Yeah, the question is, what is the parameter? You see, let's say, to give you an example, in large N QCD, it would be, 1 over N, or sometimes.
Oh, no, sorry, I'm working at weak coupling. The G is small.
No, in G small, they are the same order. Those two diagrams, unless I'm confusing, those two diagrams are the same order. I'm sorry.
Let's go back to the flat space example and make sure we agree on the flat space example. So here you could have stopped me at this point, right? In my flat space calculation, ask me why I'm not including this flat space diagram, which is same order as this one, right?
Yeah, exactly, yes.
Yeah, so here, because this resummation is really relevant when S is close to M sigma squared, and this diagram, it has, so let's say that S is M squared plus little delta, okay? So then this diagram, it's of order 1 over delta cube, right? Because all of this 3 guys around shell, while this diagram is only 1 over delta squared, right? So what we're resumming, so we're basically saying that G squared over delta is order 1, right? And this is kind of.
Yeah, that's the answer. I'm sorry, I missed your flat space part of the talk. So that's the answer. Yeah, that's the parameter that you are.
Yes. Okay, sorry. Yeah, because it's exactly analogous in.
Okay.
Okay. Any other questions? Okay. How much more time do I have? There. Well, if Massimo is saying
Massimo, you're muted.
20 minutes?
You're saying something, I cannot hear you.
20 minutes?
20 minutes, okay, good. Now, yeah, there is some, okay, the de Sitter space, yeah, let me go back. So I discussed the analytic structure of this diagram. We concluded it's meromorphic. The meaning of these poles from the de Sitter space point of view is basically quasi-normal modes of this theory in the de Sitter space. And unitarity, I didn't get really to say what unitarity is. Unitarity manifests itself as positivity of this density rho of nu in this decomposition. And indeed, we can check that these answers that we compute, they're unitary. And near the resonance, this rho of nu behaves in some way like this. So again, you see that it is, I just plotted it for some particular value of masses and coupling. So even though the coupling is small, you get the order 1 bump. So this background is basically the free theory answer. And of course, because coupling is small, for generic values of nu, you cannot really see the contribution, but near the resonance, we get this nice bump. Good. So let me go through this very quickly. So we may want to interpret these correlation functions as correlation functions of some d-dimensional, where d is just a special dimension, d equals 3 in this case, CFT. Our formula shows that the Bay operator product expansion, although dimensions of all these operators, of generic operators that appear in this operator product expansion, they turn out complex. So these complex anomalous dimensions, they may sound as something exotic. However, I want to just bring to your attention that these complex CFTs, they appeared both in the description of some condensed matter systems, as well as beyond the standard model model building, as we discussed in these papers with Slava and Bernardo. So in the condensed matter context, they basically correspond to description of weak first order phase transition. So if you have second order phase transition, you actually get a usual real CFT. If you have weak first order phase transition, it turns out it's controlled by this kind of complex fixed points, and they appear in some models, including some recent discussions of so-called deconfined criticality. While in particle physics, they appear in some proper RD description of working technical. It's a bit of a separate story, but I just wanted to bring to your attention that I think the connection is potentially interesting. Let me summarize this first part of the talk. So as I already said, the analytic structure of inflationary correlator functions somehow turned out simpler than I expected. Naively expected something like in flat space, some cuts and all this. So positivity turns out to manifest itself as, unitarity of the theory, manifests itself as positivity of a spectral density. It will be interesting to understand what this kind of positivity, what is it meaning just from the Euclidean point of view. So it's not any sort of reflection positivity that usually replaces unitarity in Euclidean theories. And sort of more ambitiously, we can try to look for some microscopic d-dimensional theory that would have the properties, these necessary properties in the spirit of some sort of DS CFT correspondence. I want to stress that even though I used some tricks or techniques developed in the context of IDS CFT, I never relied on anything holographic in my discussion. Good, and in principle, so we saw that the resonances now correspond to some bumps in our representation of correlators, and that should in principle be useful in data analysis, or at least it's interesting to see, does it really help us to analyze or look for these bumps in actual data of in the cosmological experiments. But to do this, we need to go to more realistic models, incorporate breaking of de Sitter symmetry, and in particular include the metric fluctuations eventually, which will result in some interesting theories in under de Sitter space with alternative boundary conditions for the metric. Okay, so this concludes my first part of the talk. And unless there are any other questions about it, I will switch to the second part. Okay, good. So I go back to my general picture of inflationary spacetime. Now inflation has this feature that to some extent it erases the information about what was happening below it, before it. So that's why we can have these universal predictions that do not really rely on what happens in this question mark. However, some complete theory of cosmology in principle should include the theory for these initial conditions as well. There's one point of view that, okay, if we just classically evolve the universe back, we hit some sort of singularity over here, and some non-perturbative quantum gravity effects become important, and basically there is no hope to describe it within effective field. However, recent studies of black hole evaporations, mostly in the framework of IDS CFT, revealed that non-perturbative gravitational effects can sometimes dominate in the infrared and actually can be describable within an infrared effective field theory. And so inspired by these developments, we're going to look for similar effects in the cosmological context, okay, avoiding a direct discussion of the singularity. So let me review one particular example of this ADS black hole discussion. So we took a model, we take a model of a two-dimensional asymptotically anti-de black hole. So according to this version of ADS CFT applicable here, there are two descriptions of this black hole. One is within one-dimensional quantum mechanical system that sits at a temperature 1/beta. That's why I draw this quantum mechanical system on a circle. This is a Euclidean circle that parameterizes the temperature. And another description is this two-dimensional gravity in ADS2 with the following Lagrangian. So we have here the Einstein-Hilbert term. There is a topological term. So in 2 dimensions, the integral of R is a topological term. And then there is some matter fields. Good. So the claim is that there is the equivalent descriptions. We can either have this boundary system, or we can fix the boundary conditions. That's why this boundary of anti-de Sitter space is at a fixed length beta, and then we fill in the bulk with a gravitational theory. So and the leading solution, basically, especially in 2 dimensions, is simple. So the metric here becomes this metric of ADS2. I remind you that this ADS metric that was something like dx squared plus dz squared over z squared. And the claim is the prescription on the gravity side is, yeah, we fix the boundary conditions, but the bulk will allow it to fluctuate. So now, in some interesting situations, non-trivial topologies can dominate. One of these is an example of spectral form factor discussed in this paper. So what is the spectral form factor? Spectral form factor is some special form of convolution of 2 partition functions of this theory. So you see there's some observable that involves 2 copies of the theory. So that's why in the gravitational language, so in the quantum mechanical language, we'll just literally consider 2 copies of this theory and calculate this observable. In gravitational language, you see, I have 2 boundaries and I draw 2 copies of spacetime. So naive topology, that would be, because the series do not interact with each other, naive topology would be 2 disconnected contributions. Okay, there is anti-de Sitter space, okay, Euclidean anti-de Sitter space on each side. However, there is also a connected contribution. And it turns out that at large times, at large Lorentzian times, okay, where this observable actually becomes interesting, the disconnected contribution dominates. So there is some solution of this 2-dimensional gravity, which has this form. And importantly, the solution also develops a singularity at rho equals 0. Okay, but the prescription that one needs to consider a contour deformed in the complex plane. And in this case, people are sure that this is something we should trust, because there is a quantum mechanical description and the contribution that is reduced by this, it is called double cone geometry, is actually reproduced on the quantum mechanical side. So, if that was not there, there could be some problem with ADS safety. Good, and recently people discovered many other cases where connections between classically disconnected regions of space-time emerge and actually dominate the naive semi-classical description of a space-time. Examples include so-called traversable wormholes and also replica wormholes that appear in the calculation of the late-time black hole entropy, as was discovered in these papers. And again, these replica wormholes that are basically connections between different copies of our system. Good, so now in cosmology, we lack a precise tool like ADS CFT, which will basically tell us that, okay, we need to look for some of these unusual contributions in our system. However, we go from the opposite direction. We assume that the same rules working on the gravity side apply. In particular, the prescriptions we're going to use, we're going to fix, remember my relation between boundary of ADS and the reheating surface in cosmology. So if in ADS, we were fixing the boundary conditions on the boundary of ADS, now in cosmology, it's natural to fix the values of the fields as this, what we call reheating surface. And then the past, we're going to fill with dynamical gravitational space. So one early example of such logic is the Hartle-Hawking wave function in de Sitter, or also in a slow roll inflation, where basically the idea is that we fix the value of the fields on the reheating surface, and then there is a solution of this form. This is just four-dimensional de Sitter space. And Hartle and Hawking, they proposed to take a contour that first goes along the real time and then turns into a complex plane, okay, and smoothly caps off at this point. So here there is a Euclidean part of the geometry. Very nice. So now we will consider a toy model for inflation, which is the de Sitter version of this two-dimensional gravity. Okay, so the Lagrange is very similar to the ADS-JT, to ADS gravity. This is also sometimes called Jagiv-Teitelbaum gravity. So there is a topological term, and then there is the Einstein-Hilbert action, and then there is some matter, and for matter, we're going to take some conformal field theory. So the analogy here is that the dilaton phi basically plays a role of the inflaton, and matter fields, they play a role of CMB radiation. In particular, the generic solution at late times has this two-dimensional de Sitter metric. The dilaton grows exponentially. And what we do, we say we have this period of exponential expansion, which is our inflation. And then at some given value of the dilaton, we end inflation, we put our reheating surface, and then we just transition to flat space, where we also turn off gravity because it is not so important. The sun. Good. And the matter fields, they get created in this inflation region. They simply propagate through the reheating surface. Good note that in cosmology, it's very natural to consider observables that involve, so to say, two boundaries. Because to calculate any correlation function, we always need both bra and the ket of the wave function of the universe. So we study an observable of this form. So here time goes downwards, here time goes upwards. This is basically the bra and the ket of our universe. And we fix some long modes, some long classical modes on these two boundaries. In particular, it is natural to fix for classical variables, we easily fix its value and its momentum, which prompts us to take the following Fourier transform of the convolution of the wave functions. So note that this object, technically, it is very similar to the spectral form factor calculation if we basically relate each partition function with the insertion of a wave function of the universe. Another situation where this object has appeared was in our work with Leonardo Senatore on regulating the infrared divergences in the Sitter space. There it turns out that it's also very natural for this long modes of scalar field in that case to consider this probability distribution in phase space, which is obtained by this kind of symmetric Fourier transform. And here now, instead of fixing this long modes of scalar fields, we fix the long modes of the metric. Okay, good. So as in the case of the spectral form factor, there are two contributions. One is what we can call Hartle-Hawking contribution, where just we have two disconnected parts. For each of them, the metric is the Sitter space, where we can take this kind of complexified contour. But there is also something what we call the bracket wormhole. Okay, so it is a single connected contribution directly for our observable. So here, you see we have the bra and the ket, this sort of two virtual copies of our reheating surface, and the complexified contour drawn on this picture connects bra and the ket. Very good. Importantly, that for large universe above some critical value, this bracket wormhole dominates the contribution of Hartley-Hawking. So it really provides the dominant contribution to the state of the universe, even though it is suppressed by this factor e to the minus phi 0, which is basically e to the minus de Sitter entropy. Okay, it is enhanced by the matter contribution, which scales in the following way with the size of the universe. C is the central charge of this matter field. Good. So the claim is that in this toy model of inflation, this is really the dominant contribution to the state of the universe. So it may appear that this bracket wormhole produces some sort of mixed thermal state for our CMB radiation. So why does it happen? So if we go to conformal coordinates, okay, so this is, I just transformed from T to conformal time eta for the metric over here. Then we can cut our contour in the middle, what I call the throat of the wormhole, and say, look, if we just look at this part of the contour, okay, maybe it's more proper sort of to, arrow goes this way, to look at this part of the contour, doesn't matter. It looks in the following way. We have some Lorentzian evolution. This is basically our period of inflation, okay? Then we have some Euclidean evolution. This happens over here in the throat of the wormhole. And then again, there is some Lorentzian part, but what this produces is just the half of my contour basically produces a thermal field double state between state of my fields on the reheating surface and some emergent region of space-time that we call the throat of the wormhole. Okay. Again, all what we did, we found some other contribution of the gravitational path integral to the problem with given boundary conditions. Okay, the boundary conditions we're interested that describe the classical universe after the reheating surface. Good. Nevertheless, this is a little bit of a naive impression. In fact, this state created by this bracket wormhole is a pure state. And this happens because if we try to calculate an entropy, say we take some region over here. Okay, I mean, it's the same, right? You understand, here I glue. This is just a Bryan ket of the wave function. So if we take this region that we can call A and try to calculate entropy as A, it will naively, it will look like a thermal entropy, right? Because it's just a thermal state. But in fact, there is an so-called island contribution, which appeared in the recent calculations of the black hole entropy. So long story short, this throat, this new emergent region of the universe, which we call the throat of the wormhole, it is basically like a black hole interior. So there is some sort of island that develops in the entropy calculation. Okay, that I can review this technology. For now, I just want you to believe me that the entropy calculation of any region of our reheating surface is always roughly bounded by the de Sitter entropy. Okay, this is an outcome of some proper calculation of entropy in this setup. Moreover, if we calculate the entropy of an entire universe, it turns out to be 0, which is one of the indications that the state is pure. Very good. So it's a microscopic level, the state is pure. But simple observables like the power spectrum of our CMB radiation in this model actually sensitive to the thermal nature of the solution, especially at low momentum. So there's all some infrared effects that become important at long distances. In particular, just the power spectrum of our matter fields, okay, which is the analog of the primordial fluctuation of this model, instead of being a scale invariant, it would be predicted by the naive inflationary picture or by the Hartle-Hawking state, it actually looks thermal, which in this case is 1 over k squared. Okay, so remember I'm in 2 dimensions So in 2 dimensions, the scale invariant power spectrum is just 1/k. But instead here, if we were observers living in this 2-dimensional universe, we would have observed at long distances 1/k squared. So it is something concrete and visible in simple cosmological observables. So first, okay, so that was all 2-dimensional for now. However, let's remember that this JT gravity model is actually related to a homogeneous approximation in 4-dimensional gravity with this S1 cross S2 special topology. And in principle, it would be interesting to build actual phenomenological models for initial conditions based on these bracket wormholes in 4 dimensions. Okay, let me conclude. So in the first part of this of my talk, we constructed a formalism that allows to calculate inflationary correlation functions and exhibit their fundamental properties like singularities, unitarity, and operator product expansion using some powerful ADS techniques. In the second part of the talk, we discussed some new saddle points of gravitational path integrals. For now, we only control the saddle points in some 2-dimensional toy models, but the real question is that they can actually be important building blocks in our theory for beginning of the universe in the real world. And yeah, I want to stress that both of these developments, they lead to observational predictions, as well as provide some hints on our way to the fundamental theory for cosmology. And then do I have a couple more minutes? I could mention some future directions, so maybe it's better to stop at this point.
Yeah, if you can do it in a minute or two.
Yes, yes. It's just one slide. It's basically, I already mentioned some hints of future directions in this program. I just wanted to summarize them here. Regarding the first part, we should, of course, first of all, apply our new representation of inflationary correlators to some phenomenologically relevant models of inflation, which is basically a technical calculation that can be done, and see how useful they are in data analysis. And secondly, our understanding of operator product expansion, unitarity properties, and other analytic properties, they basically paves the way to applying something like conformal bootstrap that is trying to write a set of equations that can result into constraints on the space of allowed inflationary models, as was recently very successfully applied in the context of conformal field theories like Ising model and ON model and others. Regarding the second part of the talk, as I already said, it's very interesting to construct some 4-dimensional bracket wormhole solutions and see if they can actually dominate the state of the universe in some realistic models. And another set of ideas that there should be some avatar of these non-perturbative effects in the static patch observer's way of looking on the Sitter space or on inflationary space-time, and that should give us some more hints on the interpretation of the Sitter entropy. So as you saw, for now, in our toy model, the interpretation of the Sitter entropy was that the basically maximal entropy of matter fields, or CMB radiation, if you like, is bounded by the Sitter entropy. And finally, I just want to say, so there were these two disconnected techniques, but eventually it looks like there is some relationship that emerging between the two approaches. So I guess the goal is to understand what this relationship is between the Euclidean quantum gravity approach and this more perturbative bottom-up techniques, and see if it gives us any hint what the more optimal and fundamental description of the cosmological space-time should look like. Okay.
Thank you very much.
And here.
Thank you for the talk. And now the floor is open to questions. So please do ask.
Just a naive question. so how much has been checked for that duality between the dilaton gravity in 2 dimensions and quantum mechanics that you alluded to? I'm talking about a simple check. For instance, in 4 dimensions, 4-dimensional CFT versus 5-dimensional EDS gravity, you calculate simple things on the gravitational part, such as, tree-level propagator, and then that miraculously matches, one loop TT correlation function, as you know. So something like that has been done here. The reason I'm asking is because that's not even gravity. I mean, it's not even Einstein gravity, although you called it so, right?
Thanks. So let me first of all repeat what I said, because maybe I didn't say it very clearly. So the duality is claimed to exist in this ADS setup, which has nothing to do in cosmology. In cosmology, we lack even that kind of duality. There is no suggested quantum mechanical system that would be dual to cosmology. On the cosmological side, which is really what I studied, we only have the gravitational part. Okay, just to make it clear. Nevertheless, let me, since you asked, let me just say briefly what is known about this duality in the ADS case, right? So my results do not really rely on this because I'm not doing ADS. But anyway, so first of all, this quantum mechanical system in the situations where duality exists is not really a quantum mechanical system. It is some sort of quenched disorder system. Okay, so now there are different versions of this system where something like this Lagrangian emerges. The best studied setup is the so-called Sajev-Kitaev model, where the dual part does not have, is not really this theory, because this, what I called here matter fields in the dual pair of this, at least in the conjecture dual pair of this SYK system, is a very non-local theory. So in this case, the duality exists at scales that are much longer than the horizon, than ADS horizon scale.
When you say it exists, my question is that what's the evidence? I guess.
Yeah, so people check things like 2-point functions and 4-point functions, and they match. In the approximation, if you take this 2-point function and go to distances that are long enough, where the duality is supposed to hold, it holds, which is few ADS radii. So these kind of things were checked. Partition functions were checked, and in particular, this spectral form factor that I described here is also considered a very non-trivial check, because the spectral form factor is a function. So this object as a function of time. Oops. So there is this y and this Lorentzian time t. You can put your system on the computer, this SYK model on the computer, and and calculate this and plot it as a function of time. Okay, and people did it, and they saw something like this. Okay, some plot that you get on the computer. And this piece over here, so this is called the ramp, is reproduced by this gravitational contribution. Okay, so this is also considered a non-trivial check, first of the duality, and second of this particular calculation. Okay, it is done in this paper over here.
Okay, thank you.
And yeah, I just want again to summarize. So in the theater, we do not have we do not know what this would be. Oh, but we start from this side and we do these calculations that we try to use the same rules. And that is our hope, is that will help us to eventually understand what replaces this thing in cosmology.
Yeah.
I have a couple of questions. Yeah. So one question is, I mean, this 1/k squared you found for low k coming from this wormhole. I mean, normally one thinks of 1/k of the scale invariant spectrum as coming from the fact that inflation has a time translation invariance or approximate time translation invariance. So as the modes are generated and as time passes, they're generated with the same amplitude. So you end up with scale invariance. How do you understand this 1 over k squared from that point of view? And then
yeah, it is.
well, why don't you answer this and then I'll ask the other question.
Yeah, okay, yeah, let me just answer this. So this is, so the actual P of k is some function that, interpolates from this at k going to 0. And then of course it goes to 1 over k when k goes to infinity. Because the way this space-time is organized, we can, well, for example, we can see it on this picture, right? That short modes, they of course only care about what happens near the few last e-foldings, and here the metric is basically the Sitter metric, so the argument about scale invariance applies, right? So when we get this 1 over k squared piece, it's just a sensitivity to this Euclidean part of our contour. So this is just a thermal spectrum of a massless field. So we have, so our fields, they just leave, I mean, they are in a thermal state, and then thermal spectrum for a massless CFT in 2 dimensions is 1 over k squared. So, well, it's dimensional analysis if you want, or we can derive it in some way, but there is no, I don't think there is any deeper understanding than that.
But I guess the question is, I mean, when does this happen? So if you tried to apply this to sort of a real inflationary model with
yes, good. Yeah, this is something I glossed over a bit because it's it becomes a bit technical. So you see there are some parameters in this solution, which is this B of IR, right? Mm-hmm. And they are related, but in fact they're not what I fix on the boundary, right? What I fix on the boundary is here, is the size of the universe and basically the extrinsic curvature, the rate of expansion of the universe, at the moment when I exit inflation. And also I fix phi b, right? Which is just when it's like a value of the inflaton at which reheating happens. So, right, so these are parameters, L, K, and phi b. So now this B and phi R, there are some functions of L, K, and phi b, which at this point are just parameters of the model. I mean, this is really a parameter of the model. The way we treat this at the moment is that we do not yet understand, ideally we would also want to understand sort of probability distribution for these large modes, like size of the universe. That is not how we treat this at the moment. At the moment, we just keep those fixed. We say that this is some classical observables, we measure them in experiment, and we keep them fixed, okay? So these 3 are kept fixed. So now this B and phi R are some functions of this L, K, and phi B, okay? And that basically sets the ratio of the 2, roughly speaking, sets the scale at which the modes become sensitive to this Euclidean part of the geometry. Mm-hmm. So this, what I called temperature here, I didn't want to overwhelm it too much with formulas, especially because this is something that's model dependent. So okay, in this little model we can compute, but really this T is eventually a function of this classical parameters that we have here.
Okay, thanks. So the other question was, in one of your future directions, you mentioned using bootstrap to constrain inflation, which I think what you have in mind is you can make this map to Euclidean ADS, and then there's some constraints on I don't know, the field content of Euclidean ADS coming from CFD consistency rules or something. Is that what you meant?
No, not really. It's, well, similar but different. Really, we want to calculate, we calculate these correlation functions, say, of our inflaton field. These are some correlators in Euclidean CFT3. Really, in actual inflation, it will not really be a CFT, right? It will be some deformed CFT, but let's drop this complication for a moment. Let's say we're in the Sitter limit.
But
now,
sorry, already this is where I wanted to ask the question, because I mean, that's a non-perturbative, like first you make this perturbative map to Euclidean ADS, right? Which is perturbative only. As far as
yes.
And you make another step, which is to claim that there's this number. So how do you know that this should work? I mean, why is there, how do you,
good. But yeah, let me basically finish the phrase. So now this Euclidean CFT, well, we can call it QFT if we include this break-up symmetry. It has some properties like, first of all, operator product expansion, and then say this positivity of rho of nu, that, okay, at this point, we conjecture that they should be true non-perturbatively. Okay. So now this is a bit of a leap of faith, but it is, you know, in a sense, all bootstrap, you know, especially say S matrix bootstrap. Okay, maybe the, you know, CFT bootstrap is really something that can be put on a firmer footing. But really, when we do something like S matrix bootstrap, right? This is where you infer some analytic properties basically from perturbation theory, and, you know, assume that they should be true non-perturbative. Sorry, this part, you can really argue non-perturbatively. I mean, as usual, unitarity is really a non-perturbative statement. Yeah, I could derive this part without even going to ADS, if you like. This part, yeah, I prove it through going through ADS. Looks like it's true to always in perturbation theory. Okay, we can, I know, maybe make a leap of faith and say that it's also true non-perturbatively and see if we get any interesting constraints. Yeah, this is kind of the game you can play. Of course, I mean, I don't think it will get to a level of rigor that you will, you know, see that inflation is excluded and then you trust it. But if you start getting some interesting bounds, it may, you know, it may be interesting.
But so you basically are proposing a DS QFT correspondence and then using some consistency conditions on the QFT to constrain the de Sitter, right?
Yes, yes, in a sense, yes. But we should be careful, right? What's usually labeled by the term reserved for say DS CFT is a statement about the wave function, right? Which is not really an observable. Here we're doing something that, okay, the rough level approximation may sound similar, but here we're really discussing the properties of correlation functions, which are really the observables, and that, you know, we should believe that should satisfy some physical properties, and that's what makes it very difficult at the technical level. Like this like, you know, this for a wave function, you can also associate some set of correlation functions and their properties. Well, OPE will still be there, but the structure of OPE will be very different. Operators that appear in this operator product expansion will be very different than what happens in the correlation functions. Mm-hmm. And unitarity properties will call it very differently. So that the first order in perturbation theory is almost trivial, but really when you go higher, it becomes the properties of these two objects become very different. So that, I guess, one of the changes in paradigm. But roughly, yes, yeah, we want to say that all the properties of this cosmological evolution are in some way encoded on a single Euclidean slice, and this is what we're trying to decipher by understanding things like this and like this.
Thank you. Are other questions, maybe from students or?
So may I ask? I'm not a student, but. I'm trying to understand better this non-perturbative contribution you're talking about. So, because you're saying it dominates at long times, but so assuming that it all can be lifted to 4 dimensions. So what would be the optimal situation to find trace of this when inflation lasted much longer than 60 foldings, or even lasts roughly approximately 60 folds, like usually for some like remnants from pre-inflation?
So this is, in principle, so I said that in the spectral form factor discussion, it dominates at long times. So here it equivalently dominates for large universes. So when the slice of the, you know, the reheating surface becomes large. In principle, in this model, nothing prevents you from taking universe infinite, because you know, the usual inflationary set, I would say, Harper-Hawking stated as such that universe is always compact, and roughly speaking, the size of the universe is proportional to the length of inflation. Here, the most dominant contribution, it looks like when you just produce an infinite universe, so okay, you know, as large as you like, and then it always dominates, because then this contribution over here, Z matter, formally diverges. So you right away dominate. But then it comes basically to the discussion that we were having with Matt, that if inflation lasts long enough after this, if there's sufficient Lorentzian evolution after this, you know, Euclidean piece of the geometry, and of course, as always, with inflation, you cannot distinguish. So you will, you know, the ideal situation where you will observe something like this is, of course, when this period of evolution is, comparable to 50 foldings. So we're not excluded yet, but, then you look at some, you start seeing this tail, with when you go to low L modes. So that would be, but yeah, then the hope is that the model is some realistic model will be constrained enough so it will be correlated, with some other observables, and then you may hope to decipher it. But yeah, something like this.
Thank you. Other questions? Okay, so if there are no anyone, sorry.
I have one. So the first part of your talk was you did a perturbative expansion in G or G squared, right? This coupling. Mm-hmm. But you also assumed that Hubble was constant, right? So I guess you're taking the leading order piece in H dot over H squared or something.
Yes.
So, but the effects are probably only observable if G is relatively big, right? So is it do you require that H dot over H squared is smaller than G or G squared, or do you know like when the approximation starts breaking down?
Yeah, good. So this is something we didn't yet study in details. I mean, that basically refers to this part. I mean, what I know is that there are in different models of inflation, this leading contribution to non-Gaussianity can either come from effects related to slow roll parameters, or it could, the leading one can be the de Sitter invariant one, which basically when, self-interaction of the fields that have nothing to do with gravity, interaction of, say, inflaton with some other field that is not directly related to slow roll parameters can be the dominant one. So, you could hook up a model where the diagram that I calculated would really be the, at least, the leading effect that is sensitive to this new sigma particle. Now, what you're saying, of course, we need to do a more detailed study. And in particular, there's nothing prevents us from including slow roll corrections in this framework. This analytic, at least again, perturbatively in slow roll, this trick of mine is going to work. So we will just get some integrals, not in Euclidean ADS, but instead of this ADS with some, radial, which the scale factor in ADS will also be changing, not exponentially, but with some slow roll corrections. But we can still proceed. And so it's not really a limitation of formalism, it's just a limitation of calculations we've done so far.
Thank you.
Thanks.
Any question? Any student has a question? Maybe I have one. And this, when you sum over the disconnected topology, you sum over the connected topology, but why not summing over surfaces with two boundaries and G loops? You may lose something because of the G loops, but you integrate over moduli, and as you know, the sum over Jenner actually diverges like if there is no tomorrow, right?
Yeah, so this is, again, this is an assumption in these models that those loops will be suppressed. Basically, the difference, okay, so you may say, how come? Maybe counterintuitive. So what Massimo is talking about, well, why don't we add some extra handle over here? And okay, we lose another power of e to the minus phi 0, which is some small number, but then there are some maybe extra matter loops and some moduli enhancement when we go to large G. Yes, the point is that this loop is really large. It is infrared. So for example, this I could introduce a cutoff at my theory on scales longer than the horizon scale. Okay, so basically what happens in the SYK-like models that really we only trust them on a super horizon scale, and this thing will survive because curvature never really, nowhere on this contour, I can draw this contour of mine, sort of deform it somewhere here, and curvature never even becomes, Hubble scale or something. So or the size of the universe never becomes comparable to Hubble scale. I can always feed my cutoff longer. While these guys, they will, generically be some, at least at curvature scale, or maybe there will be some UV contributions even shorter. So we can sort of have a model where these guys are regulated by some UV completion of this theory, and this contribution is still trustworthy. This is basically what we have in mind.
Thank you.
Yes, I have a question. So in anti-de Sitter, the island kind of represents the existence of a new quantum extremal surface, and then you purify the state of Hawking radiation. In de Sitter, what is the island? Because in anti-de Sitter, maybe not in ADS, but in black holes, one can understand that after the scrambling time, the information is kind of inside the horizon, and doing operations in the radiation, I could extract information from the inside. In de Sitter, what these diagrams represent?
Good. So yeah, let me. So I went through this very fast, but thanks for the question, because I maybe have a chance to a little bit elaborate on this. So the setup, I think you reviewed my setup correctly. That if I try to calculate, so the entropy of this SA, this A is like, the analogy is the entropy of late Hawking radiation. Let's draw a picture of a black hole over here. Okay, so say we have this is a black hole horizon, this is interior, and there is some Hawking radiation. It comes out, and we can here also have some region A. Okay, and we want to calculate this entropy. So as you reviewed correctly, the new this quantum Rute-Carnage formula tells us that the entropy is a minimum over various island configurations of basically SA plus S of A union the island plus the horizon area piece, right? So now what is this? How does this formula work? So this formula, okay. So first of all, this formula also follows from the Euclidean gravitational path integral manipulation. So same assumptions that I'm using in my talk go in the derivation of this formula. The formula instructs us that if we want to compute this entropy of this region A, we should include in particular islands at arbitrary configurations and extremize this entropy over various configurations of the island. And as recently was understood, for late time Hawking radiation, almost all interior of the black hole is contained inside an island, as long as we take a large enough piece of A. So here the analogy is the following. So we should think of our reheating surface as basically an outside observer of a black hole. Okay, so this is where the outside radiation comes out. Now there is this emergent, in a sense, an emergent closed universe, if you like, with which it looks like our state is entangled in a thermal field double state, because here also Hawking's calculation tells us that the matter fields inside and the matter fields outside, they are basically can be thought of as they are created by the Serble contour. So this picture is very similar to this picture. And technically calculation again goes in a similar way. That basically once this region A becomes large enough, the optimal way is to create an island over here, and then the matter starts purifying. But you see, the answer to your question is, well, we do not know. In the black hole case, we knew that something like this should have happened because of boundary description that we know is unitary. Here in de Sitter, as I keep saying, we do not have yet any microscopic picture for this. So we start from the other direction. We see that something like this happens. Okay, we see that in the gravity calculation, first thing that happens, we get this emergent universe. We create by hand some black hole interior, basically. Nobody told us that there should be this other region of space-time in cosmology, but it just comes out of our calculation. And then we purify it, the state by the island calculation. So now we need to sit down and think what does it suggest for some microscopic picture? You know, how do we reproduce it in some, maybe in some other variables that do not contain gravity? But we do not expect that to happen, if you like. Nobody, when we started out with this calculation, there was no expectation of the emergence of this picture. There is maybe one more thing again that I didn't say, that in this model, in the Hartle-Hawking state, in 2D, there is an analog of information paradox. So this is something, again, it will take me a little bit of time to explain how this paradox comes about. But what happens is that if you study the Hartle-Hawking state in this two-dimensional model, you can actually hook up an analog of this AMPS paradox. You can consider several regions that do not satisfy so-called strong subadditivity condition. So in the Hartle-Hawking state, strong subadditivity turns out to be not satisfied. It's two-dimensional. I don't want to say that we excluded arbitrary Hartle-Hawking state, but in these two-dimensional models, Hartle-Hawking state is excluded again by strong subadditivity argument. So we knew that something should come in and cure it, but there was sort of no guarantee that it will come in this form.
Thank you. Any other question? We have already had a very nice long discussion, but of course, please ask. It's early for Victor. Still 3 hours behind.
Yeah, I have unlimited time, more or less.
Okay, I think that if there are no other questions, then we'll let you go. Thank you very much for the seminar and for the discussion. Enjoy San Francisco.
Yes.
Thank you.
Thank you.
Thanks, Victor.
Bye.
Bye.
Bye. Thanks.